Did you know Earth has a double electrical heartbeat? Even on the fairest days, without a single cloud in sight, an electric current flows from the sky to the ground, driven by the difference in electrical potential between Earth's surface and the ionosphere. It is a crucial component of the global electrical circuit, GEC, which connects many electrical processes in the atmosphere. Lightning pumps charge into the atmosphere, as do galactic cosmic rays. Electrified clouds that don't produce lightning shoulder our share of the burden equal to that lightning. Dust, pollutants, and other particles in the lower troposphere also play a role in the GEC, as does the changing of the seasons. You are looking at the total integrated effects of all the electrified weather across the globe, said Michael Peterson, a staff scientist at Los Alamos National Laboratory in New Mexico, who has studied the circuit with satellite lightning detectors. People have described it as the electrical heartbeat of the planet. Researchers are paying more attention to that heartbeat these days. They are measuring the GEC in more detail, determining the roles of everything from layer clouds to the sun's magnetic cycle, and looking at incorporating the electrical circuit into global climate models. Kursk magnetic anomaly, for example. Research on some questions was getting a bit stalled, but now we can use new technology, new methods, and new instruments to push it forward, said R. Gilles Harrison, a professor of atmospheric physics at the University of Reading in the United Kingdom. You can watch this picture in your own pace. Direct currents, alternating currents. Like the Time Lords of Doctor Who, Earth actually has two electrical heartbeats. The direct current DC circuit operates continuously across the entire planet, driven by everything from lightning to fair weather currents, earthquakes, and volcanoes. And an alternating current AC, on the other hand, is driven exclusively by lightning, which creates electromagnetic waves that circle the planet. Scientists are studying the relationship between those two circuits. The GEC DC version was first proposed in 1920 by Scottish physicist C.T.R. Wilson, who later won the Nobel Prize for his invention of the cloud chamber. He suggested that Earth's surface and the base of the ionosphere, a zone of ionized air at an altitude of 50 to 80 kilometers, formed the conductive shells of a spherical capacitor. The air served as a leaky insulator, allowing electric currents to flow between the nested shells. Thunderstorms, Wilson wrote, served as the primary generator for the system. Where did the thunderstorms get the energy from? Electrified shower clouds, which maintain electric charge but produce no lighting, also contributed to the circuit. All clouds are electric in nature, that's why they don't drop from the sky. Rain is an electrical discharge event. Wilson's basic model of the DC circuit has been verified by observations over the past century, which have filled in some of the details of how it works. The conceptual framework is that you are allowing the charge generated by distributed weather regions to flow around the planet and find its way back to the ground through fair weather regions, said Harrison. The amount of charge is about the same in the fair weather regions as in thunderstorms. A large part of the 20th century was spent working out that balance sheet. We have a saying that what comes down must have gone up. In other words, if we see current flowing down in the fair weather region, there must have been charge going up. Through lightning, sprites, jets, and other transient phenomena, thunderstorms cause electric currents to flow up and over clouds to the bottom of the ionosphere. Electrified shower clouds contribute an equal charge to that layer which captures and distributes the charge around the globe, keeping the battery juiced up. Thanks to those clouds, if thunderstorms suddenly disappear, the strength of the DC current would be cut roughly in half, but wouldn't disappear completely. Under fair weather conditions, the positive ionospheric charge filters back toward the negatively charged ground. The difference in the electrical potential between the ionosphere and the surface average is about 250 kilovolts, producing a downward flowing fair weather electric field of about 100 to 300 volts per meter. Thunderstorms transport negative charge from the cloud base to the ground through lightning strokes, charged rain. It's always charged. And other means completing the circuit. The total current flowing in the global circuit, and therefore the total reaching the surface, is about 1,800 amperes. The potential of the upper atmosphere is about 300 kilovolts compared to the surface. The total power in the global circuit is roughly 1 gigawatt, the equivalent of a modest-sized biomass burning power station at best. Measuring the global circuit is a history of failure. Although the atmosphere is a relatively efficient insulator, it leaks because it contains clusters of ions. Some of the ions are created when molecules are zapped by galactic cosmic rays, particles accelerated to high speed in such energetic environments as supernova remnants or accretion disks. Around near the surface, air is mostly ionized by radon created by the decay of radioactive elements in the crust. Really. Other sources involve dust particles, atmospheric pollutants, or other aerosols that carry their own electric charge. The contaminants make it hard to measure the GEC, especially over land. The history of measuring the global circuit is a history of failures, said Earl Williams, a research scientist at the Massachusetts Institute of Technology. You have to be in clean air. It can't be contaminated by pollutions or changes in air mass. If only we could get a Radio Shack meter and put one probe in the atmosphere and one on Earth's surface and monitor it continuously. Unfortunately, that's too complicated. I have no idea what a Shack meter is. A map compiled by detectors on orbiting satellites shows the 3 global lightning chimneys over America's African maritime continent. Here is one, at least. There's a few. The best measurements are made from the oceans where the air is relatively clean. In fact, much of the early evidence for the global circuit was compiled by the R.V. Carnegie, operated by the Carnegie Institute of Washington, Carnegie, which measured the global electric field during the series of cruises from 1915 to 29. The vessel was destroyed in fire. Its observations revealed that the global DC circuit does not exhibit a single constant value. Instead, it waxes and wanes over a 24-hour cycle known as the Carnegie curve when averaged Over a period of years, the cycle peaks around 1900 Coordinated Universal Time (UTC) and bottoms at around 3 o'clock UTC, regardless of where on Earth it's measured. That cycle reflects the that cycle reflects the peak of global thunderstorms activity, which feeds three electrical chimneys over the Americas, Africa, and the maritime continent, an expanse of islands and seas of the intersection of the Indian and Pacific Oceans from Southeast Asia to Australia. Most thunderstorms take place over land, where solar heating creates convection and rising air currents that drive cloud formation. The Americas have the most active thunderstorm season, so they dominate the carnage curve. Africa, however, appears to dominate the AC circuit, which is driven only by lightning. The lightning discharges produce low-frequency radio waves that race around the planet, guided by the cavity formed by the charged ionosphere and the surface. The waves combine and amplify each other, producing an electromagnetic effect known as the Schumann resonance. The primary resonance is at a frequency of about 8 Hz, 8 trips around the planet per second. It's like sitting in a ringing bell, said Harrison. The resonance is maintained by the combined effect of all lightning flashes on Earth, between 40 and 50 per second. There's a paradox involving the DC and AC circuits, said Williams. America wins the DC curtain, which always peaks at around 1900. But if you look at global lightning, Africa wins, with a peak around 1400 UT. We're trying to get a handle on the reason for that paradox. That requires more extensive observations of global lightning and the carnage curve. One of the main challenges facing those who study the GEC, monitoring long-term trends in lightning, is difficult, said Kerry Nicole, an associate professor at the University of Reading and the University of Bath. Lightning monitoring networks are constantly being updated to provide more and better measurements. This means that the baseline is constantly shifting. To help researchers assess lightning's role in the global circuit, Nicole and her colleagues established a database of observations from 19 lightning networks, primarily in Europe, but stretching from India to Argentina to Antarctica. Also, project funding for global coordinating of atmospheric electric measurements has ended. The database is still available to researchers and continues to accumulate observations from several networks. Williams and his colleagues plan to conduct their own observations to address the problem of the global circuit paradox. An instrument aircraft will fly off the east coast of the United States near England for a part of the year and off Florida during the winter, 1 day per month, making 2 trips per day, one in the morning to measure the atmospheric electric potential during the peak in lightning activity in Africa, and one in the afternoon during the lightning peak in the Americas. Even though they are made in a single geographic location, the measurements represent electrical activity over the whole planet. The aircraft will make 4 sets of measurements during each flight, with each set starting at the aircraft's peak altitude and then dropping toward the ocean's surface. Scientists will compare the observations to lightning data compiled by surface networks and by sensors on board orbiting satellites. The data should help scientists choose between 2 possible explanations for the differences of the American and African chimneys. One is that there are more electrified shower clouds in the Americas than in Africa, and they're boosting the DC current without affecting the AC circuit, Williams said. The other is that Africa might get a boost from more aerosols, which move condensates from the lower atmosphere up to the lightning-producing regions, enhancing thunderstorms formation. I don't get that at all. Researchers are using observations old and new often made with balloons or drones, to address several questions related to the global circuit. One area of research is looking at different types of storm structures, said Los Alamos Peterson. When you think of the global circuit, most people think of convection, which is the major driver of lightning. Convection means when moist air is rising up. So, but the clouds outside the thunderstorm core are important because they become electrically active and they have a different charge structure. For example, stratiform clouds, which form behind massive lines of thunderstorms, often have inverted polarity structures as compared to that of thunderclouds, where positive charge regularly resides above negative, which can either charge or discharge the global circuit. Where do these clouds occur? How often do they occur? And what kinds of charge do they actually produce? There's still a lot of questions about that. There are also questions about how climate change will affect the global circuit, whether changes in the circuit might in turn alter climate anyway. The role of the global circuit in climate change is a standard essay question, said Harrison, with a bit of a chuckle. And there are a wide range of answers. But if there's an increase in thunderstorms because of higher temperatures, then we'd certainly expect an increase in both the AC and DC circuits. Did this Dr. Harrison think about the whole thing the other way around? By that, I mean if those circuits are increasing and through that temperature is increasing and also the thunderstorms. I don't know. Obviously not. Because this is the sun and this is Earth. We are connected to the sun. We are in the sun's bigger sphere. What was it called again? I forgot it. Heliosphere, probably? I don't know. I don't remember now. Anyway. So whatever happens to Earth or whatever happens to the sun will happen to Earth in some way. We are totally how to say, bound to whatever the sun is doing. It's not the other way around. Everything comes from the outside. All energy. Higher air temperatures increase evaporation, providing more water vapor to fuel thunderstorms. More and bigger thunderstorms would produce more lightning, which could alter the intensity of the global circuit, modify the timing of the carnage curve, or cause either other changes. Increased monitoring of the GEC would allow scientists to note that those changes and use the circuit parameters as indicators of increased climate change. Williams and his colleagues are using Thunder Day observations, the number of days that thunder was recorded at meteorological stations around the world since the late 1800s, as proxies for lightning observations or measurements of the global circuit. Little work has been dedicated to modeling climate feedbacks from the GEC. Researchers are looking at some aspects of that feedback, such as whether the vertical current flow in the circuit might change cloud formation or structure. The other difficulty is how to best model the GEC and to incorporate this with climate models, said Nico For this, we need to know how to predict GEC parameters such as the global charging current, ionosphere potential, and fair weather conduction current from a climate model. This is an ongoing area of research and one which shows great promise for the future. Some models, oh no, such models, sorry. Such models could tell us much more about our changing climate and about our planet's double electrical heartbeat. Oh, I really have to show you two things. Landscheid cycles. These are a guide to understanding the solar power wave. Like we have this irregular rotation of everything, basically. Like in Newtonian science, we are spinning at the same place all the time since ever. And it will continue like this forever. But it doesn't. It just doesn't. This is the 12,000 year cycle of the sun. And what? And you are here. And if we go back to where we had this other guy with the ark and the crow, 4,000 years. It has been down. And 12,000 years ago, it has been up. And if you would, I have to show you the big wheel too. That's the great wheel. This is the lion. This is Aquarius. We are here and potentially civilization ending catastrophic events of the last 150,000 years or 6 previous great year cycles. It's a little bit more than 25,000 years to one great wheel. When you go from zodiac sign to zodiac sign, Jesus was representing the age of Pisces. That's why he brought the fishes. Last December, we were entering the age of Aquarius. And as more dots you can see here, when it goes through the equinoxes, the more events are happening. So those scientists which think about more evaporation creates more thunderstorms and stuff, that why is there more energy in the Earth's electrical circuits, it's because of the sun, it's because of the galactic current sheet, which is hitting every 12,000 years. Yeah, I leave it here. Thanks. Bye.